This slide highlights the three core components that drive LLM cost and performance: embeddings, attention, and feed-forward layers. Embeddings turn tokens into vectors, attention captures relationships across the sequence, and feed-forward layers do most of the heavy per-token computation. Together, they explain where memory use, latency, and scaling bottlenecks come from, and why understanding these trade-offs is essential for both real-world LLM engineering and technical interviews. This topic matters because it maps directly to how employers evaluate real-world AI judgment. They want to know if you can connect system architecture to cost, understand where latency actually comes from, and explain trade-offs clearly instead of just repeating formulas. Those skills show up across LLM engineering and inference optimization, model evaluation, and applied research, and also AI product and systems design, where practical decision-making matters as much as technical knowledge. In Chapter 1, we'll take a high-level look at the transformer architecture and why it became so important in modern AI. Rather than processing words one by one, transformers use attention to weigh relationships across an entire sequence at once. This makes them powerful for language understanding and generation. By the end of this chapter, you'll have a clear mental model of the main components and how they work together. The key idea here is the shared width principle. In a standard transformer, every sublayer uses the same model dimension, D model, which makes residual connections possible, and also shapes every complexity formula. The embedding layer maps tokens into that shared width, self-attention mixes information across positions, and the feed-forward network transforms each token independently. So the big distinction is this: attention scales with token interactions, while feed-forward scales with representation width. In Chapter 2, we'll focus on embedding layers, which are a core building block in many modern machine learning models. Embeddings let us represent discrete items, like words or tokens, as dense numerical vectors that capture useful patterns and relationships. In this chapter, we'll look at why embeddings matter, how they're learned, and how they help models work more effectively with language and other structured data. This slide highlights the trade-off in embeddings between parameters and compute. The embedding table can be very large because its size scales with vocabulary size times hidden dimension. So, with 50 to 100,000 tokens, it becomes a major part of model memory, but computationally, embeddings are cheap. For each token, inference is basically just a lookup and retrieval step, much lighter than the matrix operations and attention layers that follow. One easy detail to miss is that embeddings aren't only about mapping tokens to vectors. Models also need a sense of order. The original transformer used fixed sinusoidal positional encodings, which don't add parameters and can generalize to longer sequences. Many newer models use learned positional embeddings instead, with a fixed maximum length, and more modern approaches, like rotary embeddings and alibi code allo position, and tend to work better for long context behavior. In Chapter 3, we turn to self-attention and one of its biggest practical challenges: quadratic scaling. Self-attention is what lets a model compare every token with every other token in a sequence, which makes it powerful for capturing context. But that same all-to-all comparison means the computation and memory grow quickly as sequences get longer, creating a major bottleneck for large models and long inputs. Scale.product attention is the core attention mechanism in transformers. It works by comparing every query with every key, producing a full n by n score matrix, so each token can attend to every other token. Those scores are then used to weight the values. The trade-off is cost. Computing these dense interactions takes O of n squared d time, and storing the attention matrix requires O of n squared memory. This is the quadratic bottleneck in practice. As sequence length doubles, the number of token-to-token interactions grows by about 4 times. because dense attention compares every token with every other token. That n-squared scaling makes long context inference, especially at 128K tokens and beyond, expensive by design. It also drives up memory use and KV cache size, which limits batch size. Techniques like FlashAttention and linformer are designed to reduce exactly this bottleneck. FlashAttention gives the same mathematical result as standard attention, but it reorganizes the computation to fit the hardware better. Instead of materializing the full n by n score matrix, it uses an I/O-aware tiled algorithm that cuts expensive reads and writes to high bandwidth memory. So even though dense attention is still quadratically scaled in theory, the implementation is much faster in practice. That's the key interview insight. Asymptotics matter, but memory hierarchy matters too. Multi-head attention changes how the model uses its width, but not the core scaling story. The embedding dimension is split across heads, so each head works in a smaller subspace. That lets the model attend to different patterns in parallel. But if the total model width stays fixed, the overall computation still has the same dominant order, O of n squared times d. So more heads change representation, not the quadratic dependence on sequence length. In Chapter 4, we turn our attention to feed-forward networks, one of the foundational architectures in neural networks. These models move information in a single direction, from input to output, without feedback loops. As we go through this chapter, we'll look at how they're structured, how they learn from data, and why they remain such an important building block in modern machine learning. The feed-forward network works on each token independently. So, unlike attention, there's no token-to-token mixing here. That means its compute is driven by width, not sequence length. In most transformer models, the hidden dimension follows the common 4 times rule. DFF equals 4 times D model. In practice, libraries expose this as intermediate size. If you increase that value, you widen the bottleneck layer and raise compute proportionally without introducing any sequence interaction. This slide highlights the key trade-off between feed-forward layers and attention. Feed-forward transforms each token independently, so it tends to dominate compute at shorter sequence lengths. Attention, by contrast, mixes information across all token pairs, so its cost grows much faster with context length and becomes dominant on long sequences. That distinction really matters, because it explains why optimization strategies often target different parts of the model depending on the workload. In Chapter 5, we're focusing on the 3 equations you really need to know cold. These are the core relationships that will come up again and again, so the goal isn't just to recognize them, but to understand what they mean and when to use each one. As we go through them, pay attention to the structure of each equation and the role it plays in solving problems. Here's the quick interview cheat sheet. 3 equations to remember. First, embedding parameters scale with vocabulary size, so they mainly affect memory footprint, not how runtime grows with sequence length. Second, attention compute grows quadratically with sequence length, which makes it the main long context bottleneck, and why techniques like FlashAttention matter. Third, feed-forward compute scales linearly with sequence length, and at moderate lengths, it can dominate when the model is very wide. Welcome to Chapter 6, Portfolio Project. Prove it empirically. In this section, we'll move beyond theory and focus on evidence, using data, observation, and testing to support our conclusions. The goal is to show not just what we think is true, but what we can actually demonstrate. As we go, keep in mind how empirical proof strengthens both analysis and decision-making. The key step is building a small benchmark project that connects the math to actual profiler traces. Use a minimal transformer harness in PyTorch with MultiheadAttention and scaled dot product attention, so nothing important is hidden. Then sweep sequence length, model width, feed-forward size, and vocabulary one at a time. Measure latency, memory, and throughput across dense attention, SDPA, and FlashAttention, and plot the real scaling curves against the theory. The big takeaway is to speak the language of model efficiency. Embeddings scale with vocabulary size, so they mostly affect memory, not runtime. Attention is the long context bottleneck because compute grows quadratically with sequence length. Feed-forward layers are often the main cost at moderate lengths because they scale with model width. And tools like FlashAttention don't change the math. They improve I/O. This architecture to cost reasoning is exactly what hiring teams look for in LLM candidates.